you'll probably want one sheet of paper for number 29, not a lot of paper for 30, 31, and 33, and at least half a sheet, if not a full sheet, for number 32. Let me try this again. I have instructions for you that are supposed to be helpful. You'll need to leave some space. If there's words you can't read, I'll tell you the words. But leave a lot of space. These are just the beginning of the notes. Since most of you don't know, you'll be writing a whole bunch of stuff. This is just what I need to remember what I have to say. You'll probably be writing something after each of those words. I can give you about 6 minutes.
What? I'll be the entire thing.
What? Are you asking what I just said?
She was asking, should we copy it all down right now, or should we do it as you go?
Good.
Copy as much as you can in 6 minutes.
Good. You guys know the drill. Please rise for the pledge of allegiance. Ready? Pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. All right, guys. We are currently in day 3 of the student auction, and our buttery contestants are selling like hotcakes. So get out there in front of the theater at lunch and throw your bids. Also, don't forget to check out the contestants' pictures and short biographies posted in the hallway of the theater where they've always been. That's right. Get on any of the contestants, and you don't
Right what you can. Right what you can. I'll go over it all.
All right, now here's a special announcement, guys. Hey guys, this is Aaron, your ASB President Imitator, and one of the board directors of this season's Music of the Night. Music of the Night is a completely student-run production that gives all the singing, dancing, choreography, costuming. It's all done by students. It's playing this Thursday, Friday, and Saturday at 7. Tickets are $10 for students, and they're free for gold card members. So please come on down to the theater and support your fellow students. Thanks. All right, thanks, Aaron. Perfect. Next up, this February 15th, the Blind Tiger on State Street will be hosting a benefit concert for senior Gracie Fisher. This event will be free, will have free entry for all ages, so be sure to mark down your calendars February 15th. It's to a fantastic cause. Finally, this Friday is the big game against SN. You guys know how it is. Be there or you're blowing it. Also, if you have not joined the Santa Barbara High School Screen Team page on Facebook, be sure to join. It's going to be just $1 for all students who have their ID and who are obviously repping olive and gold. Okay, last few items, guys. Attention seniors, go to room 206 and check the list outside the door to see if you have qualified for NHS or CSF. Pay dues to Miss A in room 206 by February 20th. Seniors, if you'd like to graduate with seals or cords, it's important you get that done. Okay, there's a MAD application workshop this Thursday, so tomorrow and Friday at lunch and after school for students who are interested in applying. You can use madacad.com if you can attend the workshop, and the application format is due the 31st. Students, AP exams can now be ordered and paid for in the business office at lunch and after school. Instructions and the AP calendar will be sent to AP classrooms this week to your section. And all seniors who have passed an AP foreign language exam with a 3 grade or better, or Santa Barbara City College Foreign Language 104 course, please go to the testing office, as you may qualify for the California Biliteracy Seal on your diploma. And finally, seniors, we got a lot of stuff today. Don't forget about the Jostens Senior Assembly tomorrow in second period. This is for all seniors who will be excused from class, although you should check in with your second period teacher first. You're going to get lots of important information about prom, grad night, and stuff like that. So thank you guys very much for listening. Have a good one.
There's 2 more minutes left for you to copy.
solar? So 29.
Don't you have distilled water down in your storage?
You could check, but unless the lid is sealed, I would assume it's just been refilled with drinking water. You can check.
Do you have your key?
All right. Please put your pencils down. Oh, really? Put your pencils down. For everybody who was struggling to get that down, I'm sure that you got at least the basics on this half. And we're going to talk about that for quite a while today. So far today, we're probably only going to get maybe this far. So I'm not too stressed out about how much you copy, but you will need your attention for a few other matters, so please put your pencils down. Well, there's an after-school environmental film tonight. There's an after-school environmental film tonight that I have to warn you, unfortunately, honestly, is kind of biased and narrow in its spectrum. It's about the coal industry, but it's based in a part of the Appalachian Mountains where people in that neighborhood are really opposed to more coal extraction, and they're really grumpy about it, and it's basically like a social upheaval kind of movie. It's about like political unrest, and a lot of my students think it's just kind of like, okay, so some Appalachians are over it, and the movie's basically about how some Appalachians are over it. It's not really a global interest film, it's about this small community protest issue. They do talk a little bit about the global issues around coal, and so I think it's useful in that sense, but I wanted to give you fair warning about that. Second, did we talk about how a turbine works yesterday? Did we talk about the 4 types of coal?
Yeah.
Did we talk about that very dirtiest type of petroleum?
Yeah.
And did we talk about the gasoline tax?
Not petroleum, aeronautic tax.
Okay. So really quickly, I want to do study number 28, please. It is the shortest and simplest answer. Two days ago, the warm-up was. 2 days ago, the warm-up was, what would happen to gasoline sales if you raised gasoline taxes? And the answer is probably the obvious part that you think. In the long term, if gasoline becomes more expensive, what happens to gasoline sales? Go down a little bit. Right. And my study goal number 28 says, what's the debate? Why raise it? Why lower it? And there's like, yeah.
Well, if you raise the gas of petroleum, the price of petroleum, the more expensive ways of paying petroleum, is that more?
Yeah. So as a separate issue, that makes effective. That makes worthwhile the most expensive source of petroleum. That's true. But separately, if gasoline prices go up, people buy less gas. So the Prius had its explosion when gasoline prices peaked. And coincidentally, American auto manufacturers can't keep up with demand for SUVs right now because the American public doesn't really think very carefully. They're like, gas is cheap, who cares about mileage? And they'll buy SUVs. Just so you know, among all economists everywhere, there is no doubt that raising taxes discourages behavior, and subsidizing costs encourages behavior. You subsidize the things you do want, and you tax the things you don't want. The whole debate about the gasoline tax is whether our economy or our environment are the biggest priority. It's not a debate about how the tax works. It's about which part we really want to pursue. Everybody understand what I'm saying here? Then I'd like to switch gears to assignment number 7.4, which will get us into this today, I promise, but we're still catching up with other periods. So please don't stress about the diagrams. They'll be on the board for days to go. That's for you. So, in the vocab for 7.4, do I need to help anybody with renewable, non-renewable, and biofuel? Then could somebody tell me what the warm-up was yesterday? Can you light your farts? Can you light your burps? And is anyone here, aside from myself, qualified to answer that question? Oh, Jay! I'm glad. Your generation has really lost something. I'm glad there's a few of us that are still willing to experiment. Jay, tell us, is it possible to light one's farts on fire? Yes. You know for sure? For certain? Yes. How would one know this with such great conviction that it's possible? You saw it on YouTube?
That was the inspiration?
Yes, but then you... Now all of you are laughing at a man who takes risks, pushes his limits, will drop his pants to pursue science. Before you all judge him, I'll remind you that in my generation, everybody, it was like a rite of passage. You were not allowed to enter junior high, let alone high school, if you hadn't at least lit a few parts on fire. I don't know what's happening. I realize that people don't jump off cliffs anymore. They just watch on YouTube. But back in the day, the good old days, we used to all light our parts on fire, and it totally works. It's freaking awesome. You do it more than once?
In the same night, yeah.
I'll give everybody here a couple of hints. For one thing, when hot gases enter our cooler atmosphere, they rise. On top of which, flames climb. So you don't want to lean over like this to try to look, because you'll light your head on fire. You want to get everything away from the source of the gases. Or perhaps do it with the legs over. That's pretty fun. And also, your clothing does generate a sort of less effective but significant air filter, so you want to be in a safe environment where you can really explore. But oh my God, the glory is great. Praise be to Jah. It is an amazing moment. It makes a very, very, very bright blue, clean blue flame. Oh yeah. But can you light your burps? Anybody ever burp across the table at a romantic candlelit dinner, for example? No, you can't. No, you can't. Nope, you can't. Burps don't light at all. Anybody know the difference? They're both gases that come out of your body. What's the difference? Yes, one of them has methane. Your farts have methane. By the way, they have a lot of other stuff. We're behind the other classes, so I can't go into the depths that I have in my other periods, but your farts are mostly swallowed air. So people who fart a lot just don't chew their food very much. That's my problem. So if you don't chew your food very much, you make little air pockets, and then you swallow air pockets. And that's got nothing to do with smells. It's just farting out air bubbles that you inhaled while eating, that you swallowed while eating. Second of all, your farts have a little bit of decomposed sulfur. And when sulfur compounds decompose, they make hydrogen sulfide, which is also known as swamp gas. That's the stinky part of your farts. And the stinkiness of your farts depends merely on how much sulfur is in your diet. But the methane, that's an interesting part. That's the part that's flammable. And aren't you digesting stuff when you chew it? Aren't you digesting stuff when it's in your stomach? Why does no methane come out of your stomach? It does come out of your butt. Jake and I know from experience, and the rest of you should trust us. But why do gases coming from your stomach not contain methane? What's the difference? Quickly here, you gotta move on.
Stomach acid break it down or something?
No, but that's an interesting guess. There's stomach acid in there, and there's bile, and there's something else that makes the difference. Digestion is digestion, but there's two kinds. Has anybody? What? You have something? You have a guess here?
Well, like the bacteria in your large and small intestine creates the methane.
Yes.
Whereas the bacteria is not really present in your stomach.
That's right. And why are those bacteria different? You're right that it's about which bacteria. They do different types of digestion.
But they did like a bottle that I could put it in.
How are they different? This might smell like hell.
Are you talking about the two different kinds of digestion? One being chemical and the other is actual stomach acting?
No, I'm talking about two different kinds of chemical digestion. Look, has anybody ever rested on someone's stomach / torso, and when they move, you hear something like... what makes it so you hear liquid in the stomach, but you don't hear liquid in the kidneys?
Air.
Yes. Yes. Your stomach has both the bile and whatnot, but there's also an air pocket. And this is the difference. You've got to write these things down quickly because we need to catch up with the other periods. When carbon compounds decompose aerobically, they make CO2 because, you know, there's oxygen in the air. But when carbon compounds decompose anaerobically, they make methane because there's no oxygen, because there's no air. So anaerobic digestion makes methane. Aerobic digestion makes CO2.
Or burps the CO2.
So if there were dissolved or digested carbons in a burp, they would only be CO2. Technically, your burps are mostly swallowed air as well. The reason this matters is any place where carbon compounds decompose anaerobically, they generate methane. Like in a landfill, or like,
Oh my god.
or like inside of a cow's gut.
Are you not supposed to do that? Isn't it really nice?
Oh, really? I didn't know that. Wow. What if I'm blinding you right now? Too bad it's on video. It's the green lasers. This is just a way to get my students' attention. Put away the phone. It's even more dangerous if I throw it. Put away the phone. Yeah. Okay. The anaerobic digestion, that's a big deal. That's why landfills are such a giant source of methane. This is also why when we change a cattle's diet to something that decomposes more quickly, they fart a lot more. Carnivores cause about 40% more global warming than vegetarians across the board because of their contribution to the methane farted by cows. Yeah.
So what do they eat now that is fat?
Oh, we fatten them up because fat equals flavor. So instead of eating grass, which decomposes slowly, we feed them corn, which decomposes quickly, and those sugars break down very fast into methane. So we feed them fatty food because we feed them sugary foods like corn because we want the fat as a byproduct of all that carbon. They fart out huge volumes of methane. There's a lot less digestible carbon in grass. Yeah.
Would it be possible to attach a pilot light
Yeah.
to a...
Yeah. No. As absurd as it sounds, people actually have harnesses.
This is great.
Very small shielded pilot lights and a little butane source on the back of cows as an experiment to see if there's a way to lower the methane, because if you can light the farts of the cattle, then they make a lot less global warming because CO2 is a lot colder than methane gas. And so literally you can do the experiment where there's like a field of cattle lighting their farts unknowingly, and supposedly it spooks them. And so they start running around, and when they run, their stomach twitches, so they fart more. So you get this like machine gun staccato charging stampede of machine gun flame-driven cattle sparking grass across the fields. Yeah. Okay. Anybody want to talk more vocab? Before we can do that, I've got to do one slideshow, and this is a little Band-Aid to repair the missing pieces of your education. Some of you, if you remember physics, will know everything that I'm showing you. But some of you unfortunately don't know, so I'd like to show you a couple of things. Please look up. When you move a magnet past a wire, you induce a current into the wire. The magnetic field of the magnet creates current in the wire. How many of you have heard of this? Great. How many of you remember the left-hand rule and right-hand rule? Left-hand rule of how a magnet makes a current, right-hand rule about how a current makes a magnetic field. Yes? Next. With many wires, you put an equal current into each wire, and stay tuned, because here's the big logical jump. If it's a single wire wound up and the magnet touches it 4 times, there will be 4 times as much current going through the wire. So now imagine if you could make a whole lot of wire and a whole lot of magnets. Now we're getting to a key concept here. This is the fundamental of how all the world's electricity is made, with one very small exception. All the electricity on Earth, about 98%, is made this way. You move magnets past a humongous bunch of wire. The magnets are big and the wires are big. But it all comes down to this: figuring out how to spin the turbine. Please look up. Coil of wire, fancy, surprisingly expensive magnet, and exceptionally low wattage, high efficiency light bulb. We can use human power now. You can see I'm making just a teeny little bit of electricity. The amount of work we're talking about, like, I'm getting ready to break a sweat here. My arm's starting to hurt. And I've made like millionths of a watt of electricity. This is like the most efficient light bulb. It's like an $18 light bulb. But look, wind power is just one way to spin a turbine. Bigger the better. Hydroelectric dams, just another way to spin current underwater turbines, just another way to spin this one, steam. This is a steam jet. Those are steam blade turbines. So like when you go to a nuclear power plant, all you're doing is using nuclear reactions to boil water, and then the pressurized steam is doing the turbine thing, just like everything else on the planet. Every single electrical generation source on the planet is this, except for a couple of little exceptions. We already talked about fossil fuels. Coal, natural gas, petroleum, and everybody knows you can light them on fire to make water boil, to make steam to spin turbines. So that's the non-renewable stuff. We don't need to cover it, because you can make fire and then water boils. And you can probably boil an egg or seen someone else, maybe your butler making soup or something. You've seen how it works. It's such an inflammatory thing to suggest you have a butler. How dare you? I don't have a butler. I have a maid. Yeah, he has a maid. I'll call my assistant to find out right now. Now I've got to talk about the renewables. We start today, we hope we finish by tomorrow. We should have caught up with my other classes maybe by the end of the week. First, number 29 is about solar power. A couple of things I'm not going to talk about. If you don't know, you have to write things down. So you'll probably be writing a lot more than I've written on the board. This is just what prompts me to say what you write. So one thing, in case you were not aware, this is not passive solar. If you didn't know, you got to write that down. Passive solar is a way to design houses to use less conventional energy. That's passive solar. That's a separate thing. Also, this is not solar heated water. That's another separate issue. You know you can heat water, right? Like the pipes between the glass that makes hot water, like some of your neighbors might have to heat the pool or something. What we're doing here is using sunlight to make electricity. You know, light into electricity. Please look up. Light, electrical. Light, electrical. And just so you know where we're headed with this conversation, there's the solar panel thing, and then there's something different that we'll discuss separately. Apparently, my gears got rusted, so, oh yeah. Go ahead, go get the sun. Hooray! Dirty tricks. This is why they pay me the big bucks. If he makes it out the door, he can go all the way down to the garden. Okay, last try. I just found all the hair that Daisy has ever lost. Oh, make it, make it!
Come on. Put a piece of paper over the door. Oh my god.
My gods won't help me.
Put a piece of paper over the threshold, it probably would.
Shut up. There's three parts to a basic solar panel. And just so you know, there's a bunch of nerds that have made different solar panels, but there's like the generic solar panel. I'll tell you what the three layers are, then I'll explain what those things mean, then I'll show you how it works. We're going to come back over this a number of times. First of all, you got to write it all down. Number 1 is silicon with boron. Number 2 is semi-permeable electrolyte membrane. Number 3 is silicon. It's all written on the board. Please look up. 1, silicon with boron. Oh yeah, that is actually a periodic table. And oh yeah, I am going to talk a little bit of chemistry here. And you can always copy those words on the whiteboard, but some of you really need help with the chemistry, so I would suggest you really focus on one little thing. And some of you will know what I mean because you're actually chemistry nerds, and that's good for you. If you already speak the chemistry, this will be easy. Some of you know what valence electrons are. If I say 1s2, 2s2, 2p1, that might mean something to people here. Anyone? Beautiful. And I'm guessing you don't need the rest of this. For everybody else, we like to think of electrons as having layers around an atom. They're technically not in layers, it's just a convenient way to think about it. They're in clouds, I'm sure someone told you that already. Separately, boron has a very specific arrangement of electrons. Boron has 2 very close rings that are full. The 1s2 and the 2s2, those are packed. But boron has 1 loosely attached electron. If you didn't already know that, you have to write that down. We choose boron Because with a little excitement, it can lose hold of an electron. If you don't know that already, like if you wouldn't have known that I was going to say that, that has to be in your notes. Boron has a single loosely attached electron. A little excitement will kick out an electron. Special thing about boron. Next. Semi-permeable electrolyte membrane. We can break that down if we go in reverse with a word you totally know and a word you probably kind of recognize and then a word you can probably piece together. A membrane is an isolated layer, a distinct layer. That's what a membrane means. It's a distinct layer. And electrolyte, we know it's got something to do with electrical charges. You know, electrolyte drinks, they have like ions in them, you know, electrical charge stuff. So membrane is a layer, electrolyte is something to do with charges, and semi-permeable means some stuff can get through. Like the door of a club that has a bouncer, you can get through sometimes, but you can't get through other times. Hot babes, go on in. Ugly pack of unattractive men, sorry, we don't need you in this bar. That is the semi-permeable part. So, listen very carefully. A semi-permeable electrolyte membrane is an engineered membrane that lets certain charges in or out. That's the generic concept. That's what those things are. They are engineered membranes that are selective by charge. So FYI, please look up, there are membranes that allow positive charges to go both ways but not negative. There are different membranes that allow negative charges to go both ways but not positive. There are membranes that only allow neutral passage but not charged. There are membranes that only let positive go this way or positive go this way. And this particular membrane is specific, you must know, only negative, only down. In a solar panel, the semi-permeable electrolyte membrane is only for negative charges traveling down. Finally, we use silicon because silicon is a semiconductor. That means electricity can kind of go through. Kind of. It's nice because you can build it into sheets. You can like create like crystalline structures, so that's pretty handy. So, before I can make electricity with my solar panel, we all have to take a little side trip to another physics band-aid. This is like one of those little things that a lot of kids already know, but a lot of you don't know, so I got to make sure we're all on the same page really quick. What the hell is electricity? Yeah?
It's the flow of electrons.
Now we like to say it's the flow of electrons. How many of you have heard that?
No.
All right. If you want to believe that, go ahead. Because frankly, it's by far the easiest way to understand. Like, truthfully, it's a lot easier for me to teach this if I just pretend it really is the flow of electrons. So when I talk about it, I'm going to say flow of electrons, but are there any physics nerds that actually know that there aren't electrons technically going anywhere? Do you realize that we would run out of electrons on one end and we'd have a whole bunch of like jet of electrons going somewhere else? Does anybody know a more accurate way to describe electricity? Yes?
It's green superfan works better.
It's what? No, I know. I want to see it. Okay. What is it? Not really. What?
They kind of like the electrons bump into each other, sending, or not, sending motion.
Energy.
Oh.
Work.
A better way to say electricity, and this is just so that we're all on the same page when I explain this 1,000 different times, so we got to really get our facts straight. Electricity is basically the transfer of electron excitement, which sounds pretty effing whack. So let's see if we can all figure out what I'm talking about. When an electron gets excited, it, watch me, shoots further away from the atom. That's an excitement of the electron. Technically, it now has a little extra energy in the electron. It's gotten more excited. But you know, there's like attractive forces, the positive, negative, and like it's kind of like gravity, except it's not really gravity. It's kind of like gravity. Where that electron will come back to its original layer, and all that energy has to go somewhere, so it like burps out energy to a neighboring atom. So here's another way to think about it. Have you all seen the wave at like a sporting event?
Yeah.
You know what I'm talking about. Let's do it. Everyone, we're going to do the wave. Get ready, because we're going to do it. You all know how this works. Everybody knows how to wave.
Short wave.
Shut up, godless. You don't know how the wave works.
What?
You know how the wave works.
Yeah, but you want to stand up.
No, you can do it sitting down. Watch me. You can stay in your seats. Ready? Yeah, very good. Okay.
Not a very fast wave.
All right. Now. No, we're not going to do it again. Let's do it again. Let's go. Yes. We're number one. Okay. If you were all atoms of copper in a wire, when I add energy or excitement to the wire, there's a bunch of excited electrons, which upon returning to their atoms, have to put that energy somewhere, and the energy will gradually excite successive layers of electrons through the wire. And so we can say that there are electrons moving, but all the electrons stay in the atom where they were. Instead, they are merely transferring their excitement of electrons along the wire. And then at some point, that energy can be vented to do work. Current can be translated into something else, like making light or heat or something. Question?
It reminds me of the thing where like there's a bunch of balls on sticks and you hit one side of it and you
Yep.
hit the other side.
I can see why it would. It's another transfer of energy. You're onto something.
How do you excite electrons?
Oh, very white candles, like plunging necklines, I think. I don't know. What works for you? It's an input of energy, you know. So some electrons are more excitable than others. Some cannot be excited. No, really. Some are more excitable than others. Some cannot be excited. And we choose boron because it's very easily excited by sunlight. Like, back to the science. Watch. Now comes the science part. Look. My 3 layers. Silicon with boron, the semi-permeable electrolyte membrane. You can see there's little gates in the middle layer. See those little gates? Those are for negative charges to go downhill only. And on the bottom, silicon. So, we flip on my evil sun. Give me cancer. Ooh. And the sunlight excites the boron. Remember, it's easier to say that the electrons are moving, so let's move. Okay. So the electrons come off the boron, not really, but, And when they do, what charge do electrons have? Negative. Electrons are always charged negative, right? Everybody knows that? Positive. So which way will they, shut up, which way will they travel through the panel?
Down.
To the bottom, that's right. So please look up. I'm going to get all these electrons.
Are those E's?
Those are E's. I'm going to get all these electrons on the bottom. And remember, they're not actually traveling, so the excitement is piling up down below. And on the top, by removing the negative charge, which charge do I leave behind? Positive, right? By taking away the electrons, it's net positive on top. Everybody agree with me? This is like a key thing. Are we all cool with that? If that's not in your notes, you're blowing it, because now look. You've created a positive side and a negative side. Just like a battery, you connect them with a wire, the current flows, it does work along the way. Ta-da! That was almost a clap right there. No. I didn't know these things, yeah.
So for that like, what is that alarm? Like, for that body gets electric, a negative times back, how does it do that?
So this is the funny part, because you are having trouble reconciling the fake explanation with the real explanation. The fake explanation is electrons are actually going somewhere back home to the boron, right? But remember that there are, let's get real here, there's no electrons going nowhere. And so when energy enters the system, energy is passed through electrons. And it doesn't come back. It actually gets spent in the light bulb. So if you wanted to follow the energy here, it's a one-way street. There are no arrows past the light bulb. You feel me? The energy of the sunlight is exciting the boron, which is passing excitement. Now it's electrical work, right? That excitement is being spent as light and heat. But the boron is still boron, and as long as sunlight hits, it'll keep exciting neighboring electrons. Does that make sense? You know, silicon is stable. It gets this excitement from the boron. It would not get excitement from sunlight alone. Boron has this special sparkiness. It's got this one electron that sunlight is enough to shake out, and on its way back it gives off the energy. So technically, boron is the one that translates sunlight into electrical current. You gotta admit, that was a fairly detailed chemistry concept not taught as chemistry. I know that was kind of drawn out. Yeah?
How do these electrons, they get excited, but how do they move the excitement to other electrons? Like bounce into them?
You could imagine it's like you may be inspired to clap by hearing people around you clapping. The energy leaves one atom, and it basically passes energy to a neighboring atom. That's called conduction. That's what superconductors do. They conduct excitement. If you want to follow the energy through the extremely detailed sense, energy enters the electron by having more energy. It goes to further from the atom, sort of like a cyclist in a velodrome. When you give it more energy, it goes in bigger circles. Yes? And then you can imagine that if it's going to come back down, it's got extra energy to shed. Right? So when that electron is pulled back by the attractive forces of the atom's core, then extra energy is shed by that electron, and that translates to neighboring atoms. The energy has to go somewhere. It's like, whoa! It's like the flame leaving the candle's wick and traveling to the next candle.
If I was to pull back my fist and then punch Kieran,
Yes.
and then Kieran, by the force of my fist,
Yes.
hits Marlo.
Just like that. Just like that. Yes, dominoes falling is a common analogy, yes.
You want to see it spin thing?
Make a little bubble. Alright. So now, we've made electricity with our panels. What are we going to do with that electricity? Well, option number one, please look up. We can do the Unabomber style. Solar panels put electricity into a battery. Battery runs a light bulb. Hey, it's spinning. Check you out. Good job, kid. This is called off the grid. This is remote locations only. Like a sailboat in the middle of the ocean or a shack in the middle of nowhere. Yeah. Go Unabomber. This is inherently inefficient because it relies on batteries. And anytime you hear about anybody doing anything with batteries, they're blowing it because batteries suck. The best batteries in the world can give you about 45% of the electricity back. Most batteries give you less than 10% of the electricity back. Batteries are not good. So please look up. This is expensive because it's got a lot of parts. It's inefficient because it relies on batteries. It requires hell of maintenance because batteries are hard to keep up with. And so essentially, this works, but this system sucks so bad, nobody does it unless it's the only way to get electricity. It is truly the last resort. However, does anybody here have solar panels in their home in Santa Barbara? These of you are what we call, please look up, on-grid solar system. This is the future of our cities. And the way that this works, please look up, is the solar panel feeds the meter. Because you're putting juice onto the grid, the meter spins backward. You're selling them electricity. Then when the sun goes down, you take it back from them. But we got to be really specific about where the energy goes and comes from. When you are making electricity, you're loading the grid so that your neighbor is running his fridge from your extra electricity. You understand why that's so efficient? Because the wire isn't very long. From you to your neighbor's house, it's like 40 feet or something. You can hear their dog. That's not very far for the electricity to travel. So that's super efficient. We're not losing any on the way. And the power company sees that as you and your neighbor just not needing electricity so they can produce less in the coal-burning power plant. Does that make sense to everybody? Then at night, of course, your panels aren't doing anything, so both you and the neighbor are drawing from the grid, and they see the demand goes up a little bit, so they crank up the coal-burning power plant at night. This is somewhere between cheap and maybe even profitable. It's hyper efficient because it's all short distance. This is localized micro production. I'll be right with you. And this requires very little maintenance because the only thing you've got is panels, and panels last a pretty long time. As long as you brush the dust off them, there's no maintenance other than keeping your panels clean. So this rules, as long as you're in a place where they have the good meters. Yeah.
If this solar panels are so great, like Marlin doesn't even have a bill for electricity, why doesn't every house have them?
Well, because Marlin's mommy and daddy had to put up about 10 years or 20 years of electrical cost up front. So their strategy might have been, well, if we pay up right now, when little Marlin has to go to grad school, then we'll have no more electricity bill. That's a lot of money to cough up to save $100 a month in a decade.
So they're really expensive to buy it.
So you're buying in up front with some years of trade-off, but eventually they do pay for themselves. And coincidentally, if we all had the ability to cough up the money up front, and we owned a roof that got sunlight, we should all be doing this. Like in my case, my roof is like horribly shaded, and I don't own that house, and I don't have the money, so I got a triple whammy. I will not be able to do solar panel in my current house. Yeah.
Would it be like new? Can you like?
Sometimes depends on the installation. Most people, like these folks, I'm guessing they don't own their panels. Most people enter into a contract with a provider who puts the panels on your house but pays some of the money, then they get some of the sale of electricity. Yeah.
Couldn't the government just easily like install solar panels in all our houses and then they'd get off?
Not that easily, but some governments will give you a government kickback. Like California has to pay for CO2, so as long as you lower the CO2, you can just get that money up front. So California gives you your lifetime CO2 cost as a rebate on your taxes when you put in solar panels. Anybody else? Now, I don't have a lot of time, but I do need to finish the other option. I'll try not to go past the bell, but I'm going to have to hustle. Please look up. That's photovoltaic panels. That's good, bad, indifferent, whatever. There's another way to make this. Using sunlight to create heat. If you've ever played with a magnifying glass and either etched wood or lit ants on fire, you know that you can focus sunlight to generate localized heat. Has anybody here ever flown into the airport on the big island of Hawaii? When you fly in, you see these. When everybody's going, look, honey, wake up, we're there. And you can see like the dark cliff right over the coast as you're coming into the airport. There's a place where there's these big lines of mirrors. That's these. They're round mirrors that focus sunlight on a clear pipe to make really hot stuff, either oil or salt or other secret ingredients that get up to like 2,000–3,000 degrees. And if you get the plumbing right, please look up, you can store that. And there's your heat source for boiling water. In the old days, people made these round mirrors with pipes in the middle, like you see on the big island of Hawaii. But nowadays, there's an even newer idea, which is this one. Acres of mirrors that are all reflecting sunlight. They have little motors to follow the sun on the top of a really giant tower with really hot stuff in there. Now keep in mind, when you get oil up to 3,000 degrees or something, you can put it in a giant thermos, like an underground insulated tank, and then for 3, 4, 5, 6 days, you can open the valve and make steam with that. So if you had a really sunny day, you've got 2 or 3 days of electricity stored up as heat underground. This is storable. Now, it's not just flipping the switch between the coal burning and the sunlight, but now you can use the sunlight energy even when the sun's gone away, because you can store heat. Does that make sense to everybody? This is like really big stuff. It's called solar thermal. We used to use these, what do you call that shape? Parabolic mirrors. But now we're using fields of mirrors and very tall towers. There's one of these on the drive to Las Vegas. Right before you cross into Nevada, you can see one of these on the left on the California side. Yeah?
Would you say that with the on-grid that you're storing it too, because like when the sun's down, you're getting energy?
So it's storage in the sense that they owe you money or you owe them money, but the electricity is never stored. On grid, there's no actual electrical storage. Either you're using it or your neighbor's using it or your other neighbor's using it. Does that make sense?
If they use it, then you can just take theirs?
Right. Then later on, you're going to take electricity back from the grid. But there's no storage. It's like, yo, I got extra food. I'll hook you up, and then later when I'm hungry, you can hook me up, right? That's like we're storing food in the sense that I'm storing it in her gut, and then she'll feed me because she owes me something. It's not actually being stored here. That's what makes it so efficient, that when you're making it, everybody's using it. This is not quite as efficient because you're translating heat into steam, into electricity. But the glory here is you can store hot stuff. That's a really big deal.
You can also burn birds.
What?
You can also burn birds.
Yeah, and you can incinerate birds in flight, which is pretty amazing.
That's awesome.
Y'all heard of the phoenix?
Yeah.
Bird on, yes.
They found some way to like have like a really bathroom here that like so it's like all these points to like direct at one other meter, so it was like timed to however many amount of heat.
That's what this does. You've got somewhere in the ballpark of 10 to 50,000 mirrors. They're like acreage. Imagine a Captain Santa Barbara High School plus a few more blocks. And in the middle, you've got like a 20-story tower, and all of those are going, like they follow the sun, so that every bit of sunlight hitting 20 acres or whatever is being focused on the one